As always, you are A, encouraged to have your video on, so I feel less like talking to a brick wall, and B, if you have questions at any point, just raise your hand, and I will probably answer immediately, or wait a bit if I'm in the middle of something. So feel free to do that anytime. All right, so what, oh, and I should also say that I am concerned that way too many people will try to do thinking model-based projects for the research front. Diversity is encouraged and in your interests. And while I am going to give a talk on thinking models, this is not an implicit statement that these are like the only things you should do. And all right, so recent history of language models. In like September-ish of last year, OpenAI released O1, a model where they used reinforcement learning to make it good at doing kind of reasoning problems, especially maths and code. We'd already had models that could think aloud, like do chain of thought, and this made them better at problems. But the thing that was distinctive about O1 is A, previously when models were good at chain of thought, this was like in some ways kind of an accident. Like GPT-3 just was discovered to get better at things when you told it to do chain of thought after it had been deployed into the world, because it just saw a bunch of examples of like maths working, and it was able to imitate this, but no one tried to make this happen. On more modern models before O1, everyone knows that chain of thought was a big deal, and so when they had, say, human raters ask the model questions and give it feedback, often the model did some chain of thought and got positive reinforcement. And so in some sense, they were also trained to use chain of thought. It's like pretty obvious if you talk to most modern LLMs that when you ask them like a maths-related question, they will just try to answer this in chain of thought and immediately be like, how do I break this problem down? Blah, blah, blah. So like, what was special about O1? In my opinion, the thing that was special was that they rather than these things kind of being an accident or like a small part of training, they like tried actually quite hard to encourage it to use chain of thought. And secondly, they used reinforcement learning rather than supervised training. So like when GPT-3 learned how to do chain of thought, this is just because it saw some like reasoning traces on the internet, like people talking through their working, maths homework, etc. But reinforcement learning is more like you just give the model a maths question and then you tell it, try solving it. And it gets a thumbs up if it succeeds, thumbs down if it doesn't. And this is, in some ways, a much harder learning problem because it's way harder to figure out if any action you take was useful or not, because you only get one bit of feedback. But it also allows you to learn much more complicated strategies, or like much more novel strategies. And in particular, it, for, in my opinion, basically the first time, gave the models a strong incentive to figure out how to think for a long time productively. So why does this matter? At a very high level, I think you can think of the story of all of modern machine learning as computing power results in intelligence. You have a problem, you want a solution, and you throw a lot of computing power at it, and you solve it. Historically, the amount of computing power it's taken to run a neural network has been fairly low. Like, to get a single token is much, much, much cheaper than training. And so you can kind of think of this as spending an enormous amount of computing power up front in order to get a like well-optimized network that can take a little bit of computing power at inference time and perform well on a problem. But intuitively, more inference time compute should be better, because more compute is better, if you know how to spend the compute productively. And the problem was that even if you told like GPT-4, oh, you actually can think for like 20 pages, it just wasn't better than if you told it could think for like 1 page. You could do random hacks, like you could tell it, you could just run it 20 times, have it think for a page each time, and then take the majority vote of final answers or something. And this would in fact do better than just letting it think for a page. And this is like a very dumb instance of a way to spend more compute getting a specific answer. But O1 style training was, rather than needing like weird janky like this, just telling the model, you can figure out how to use large amounts of inference time compute in order to perform better at tasks. I'm just going to give you some reward. It's going to be quite hard to fake because I'm doing things like maths and coding, where that's like a pretty objective answer. So large amounts of reinforcement learning can happen, and the model will learn real strategies rather than just how to fake out the reward function. And this means that the model implicitly learns a bunch of strategies for using large amounts of inference time compute to perform better at tasks. It's not surprising that this is possible because, again, compute is the thing that makes all of modern machine learning work. But the thing that was hard about it was productively using the compute to do anything interesting. And like models just weren't very good at that because this was a task that it was quite hard to train for. And eventually people figured out how to train for it. Such that you can now use the inference time compute and get better performance. And there's now this kind of multiplicative interplay where you can spend a bunch of compute on training the model in order to make it better at using the inference time compute and give it lots of compute at inference time. And this is just a better way of using your total compute budget, often, than an enormous blob of compute for training and a tiny bit for inference, which is like what we were kind of stuck with for most of the history of machine learning. Or at the very least, that is my stylized mental model of how I think about why thinking models are a big deal, but also why it's not some like deep mystery why this was effective. Jim?
Yeah, you said that O1, like before O1, language models weren't better when they think for 20 pages instead of 1. But like I haven't read the paper, but there was this paper where they turned like a normal language model into a reasoning model just by like inserting weight when it wants to answer.
Mm-hmm.
And like apparently that worked really well. So I wonder how it's related to reasoning models.
I will touch on that a bit later, but it's a good question. Any other thoughts, pushbacks, claims that I have fundamentally misunderstood the entire field? What? Come on, surely there's something people disagree with in there. All right, resuming it is. Oh, yes. Question.
Yeah, okay, maybe one quick question. It's not really disagreeing, and it's also more on something I can't like not completely understand yet, but I've heard that basically people are talking about a new also compute dimension now, which is doing multiple generation in parallel instead of just having a very efficient super long one. Mm-hmm. And I wanted to know if you consider that really a kind of new dimensions of scaling instead of just a different test time scaling property.
So I think that is not new. Like people have, or at least for like a while, people have often when you see people report an LLM benchmark, they will actually say, like, I don't know, majority vote at 11 or something, which means generate 11 times and take the most common answer. Or in my opinion, much sketchier, pass at 10, which means generate 10 times, check if any of them are correct, and if any of them are correct, declare victory. As a mild tangent, if you're reading like an LLM evaluation and trying to decide whether it's bullshit, pass at 10 versus anything else is like a really important difference, because in pass, you give it the ability to query the was I correct oracle 10 times. In everything else, it only gets to query it once. So it is just a fundamentally easier task. And people are often sketchy about how exactly they go about doing this, and I disapprove. But yeah. So at a high level, the point I'm trying to make is compute is how you do well at tasks. And using more computed inference should let you do well unless something is broken. And this is, yeah, should let you do well unless something is broken. And there are many schemes you could have for using inference time compute well. One such scheme is just try 10 times and see what happens. Another such scheme is, I don't know, try 3 times and get the model to critique and rate each of them, and then take the best one and then adjust it based on the model's critique, etc. You often hear the word scaffold thrown around. And this is basically just what a scaffold is. It's like, rather than just letting the model think for a long time, we write some function that just queries the model a bunch of times and hope that this is overall better than just letting it run itself. There's like lots of forms of scaffold. Like I would consider just run 10 times and take the majority vote to be a reasonable scaffold. Another one would be giving the model access to tools like a calculator or Google search. Sometimes you train it to use these, but often I think you can just prompt it and it will be fine. And generally, I think that the history of machine learning is that human intelligence can normally add value if it applies itself to a specific problem. But eventually, just let compute do its magic will beat whatever human intelligence came up with. So a good example of this would be convolutional neural networks versus attention. If you want to analyze some structured data, like text or images, it is often the case that like nearby words or pixels are much more relevant for something to do with the current one than faraway things. In convolutional networks, you basically just hard code in this idea that nearby pixels are relevant, faraway ones are not, because you can only look at like, I don't know, a 3x3 square around the current point. Attention says, I'm just going to let the model spend some of its parameters learning what the pattern should look like. Sometimes it will look locally, like sometimes there are attention heads that just look at nearby words. Sometimes it will look far away if it thinks that's a better idea. And I think of inference time scaling in kind of much the same way. Like, designing a scaffold is kind of like imposing our human intelligence of how this should work. Often this can outcompete just letting a model think for a while, even if it's a thinking model. Like they can still get stuck in loops and stuff like that. But, you know, eventually I think that just let it think for a while will just work fine. And I think that we're already seeing things like, I don't know, you just give it access to tools like Google search, and it just learns to use them whenever it thinks it's appropriate and not use them otherwise. And this is better than explicitly trying to tell it when to use the tools and when not to use them. I don't know. This is like me speculating about the rest of machine learning, which is like not my field. So I'm probably wrong on at least some details here. I know some people here have much more of a machine learning background than I do. So would definitely encourage people to jump in if they have takes. But that's like roughly how I think about it. And yeah, Uzai?
Yeah, this like letting the model kind of figure out what's best for itself versus injecting human bias or knowledge. That's something I think about sometimes as well. It might be a tangent, but example I can give or think about is like neural architecture search versus, I guess, transformers. So if it is true that you can just like give a lot of compute and time to models to figure out what's best, why does neural architecture search not work really well?
Skill issue?
Maybe.
I mean, yeah, it just seems like a really hard learning problem. I know very little about the field, but it seems messy. And yeah, riffing off what Victor shared in the chat, there's this blog post from Rich Sutton, one of the like big reinforcement learning people, like 10 to 20 years ago, called The Bitter Lesson, which basically a more eloquent and concise version of what I've just been talking about, of like, oh, man, it sure seems like we keep hoping that clever ideas will work, and they keep not working, and instead figuring out how to spend computing power on things like search just work. Lol. Maybe we should actually update as a field. He wrote this in 2004. It took people about, till AlexNet before people really started paying attention. I think this was a extremely correct and prescient blog post. And would feel better about this if Rich Sutton did not think it was good for AIs to take over the light cone instead of humans. But it's a good post. Would highly recommend reading it. And very impressive to have written it 21 years ago. All right. And yeah, a final thought on this vein is I think this has interesting connections to scaling laws. So, if anyone not familiar, scaling laws are this bizarre phenomena where if you like scale up the amount of computing power or data or parameters that go into your machine learning model, the performance in terms of next token prediction loss or a bunch of other things improves very smoothly and predictably as a power law of this input. And this is kind of wild. It's just so... You just get like ridiculously smooth curves. Like if I... Let's see. If I go to the original scaling laws paper, yep, these are just, across like many orders of magnitude, extremely smooth straight lines in log space. It's wild. And we don't really know why these happen, though I think some people have theories. But I think one way I find it helpful to think about them is they are kind of an upper bound for what effectively used compute under a particular family of algorithms should look like. So if, I don't know, you're OpenAI and you've trained GPT-3, and then you multiply the amount of compute by 10, and you try to and then you're trying to see if the model is any good. You can use the scaling laws to predict how good it should be if, like, you've done everything right. Sometimes companies mess up these big training runs, like there's been various reporting of this happening at various labs, and the way I think about it is like something was broken that did not let the massive pile of compute efficiently flow and find the correct systems. And there appear to be some deep and fundamental laws of what this should look like, at least when you average at an enormous scale. So, like, if you look at the GPT-4 system card, there's a notable point. Maybe it was in the blog post. All right, there's a graph somewhere. Nope. All right, just imagine a graph of points on the predicting OpenAI's internal code base as a data set, and they made a big deal out of the fact that they were able to like predict how well it would perform really far in advance. And well, I have no idea where this blog post is. Sorry, where the graph is. Here somewhere. All right. Oh, there it is. Yeah, and they make a big deal out of the fact that they're able to take these like small models up to like 10,000x less compute than GPT-4, and plot a curve, and then GPT-4 is like almost exactly on that curve. And this is just kind of wild that you can do this. Compute is just really powerful. And you get things like data and parameters that are also inputs into these scaling laws. But I kind of think of these as just the things that you balance to optimally use your compute or something. Because if you have a given budget of compute, you could have a big model on not much data or a small model on lots of data. And indeed, people often train models that are not at the optimal ratio of data and parameters nowadays, because smaller models trained on lots of data can perform better at inference time. All right, end tangents about scaling laws. Any questions on that? All right, onwards. So yeah, so the key point that I want you to take away from all of that stuff is thinking models are models that can productively use far larger amounts of inference time compute without needing any scaffolding. So scaffolding can totally help. Okay, so why do they work? So I think for this, it's instructive to think about why normal models do not get more and more productive when you just let them think for a really long time. Anyone have any guesses for why? Yeah, Santiago?
At least in the practical experience, it gets into loops. It starts saying the same thing. It doesn't know how to, doesn't start doing certain things that are long.
Yep, I like it. Golden loops. Jake?
Yeah, I would say something in like the same line where they over-index on like initial reasoning and then just assume that the initial reasoning is correct and then have no way to correct themselves.
Yep. Agreed. Some other ones I'd add, or rather, shifting slightly into just what do I think it would look like to design an optimal scaffold for an LLM? I basically want it to take a problem, consider several possible options it could take, evaluate them, pick the best one, follow that strategy. At each step, kind of follow this, consider several options, consider the best one, recurse. I'd want it to repeatedly check in on, like, do I basically endorse what I'm doing? Am I making good decisions? Is this a mess? And I'd want it to, yeah, kind of try to work all of this together into, and then like backtrack if it realized it was wrong, to address the like loops concern. If it knows any relevant factual information, kind of like prompt itself to elicit this, and then say it or like quote it from the question. So now it's like in the recent context window and can be used. I think that's like another very key intuition for why chain of thought is a helpful form of inference time compute, because often problems involve many steps, and if you can break it down into doing each step one at a time, this is just algorithmically much, much simpler than trying to do several steps at once, because ultimately a language model only has so many layers, and if you want it to do two steps at once that need to happen in order, it can only spend like half its layers on the first one and the other half of its layers on the second one, which is just like much more constrained than if it can spend all its layers on the first one and then all its layers on the second. So you also want it to learn habits that like let it do problems in as bite-sized a way as possible. And there was this fun paper from Mat 7.0 that I supervised from Konstantin and Ivan. And this was basically, well, this is like a kind of out-of-date workshop version, but has some of the interesting ideas, where they were basically doing model diffing on LLMs and their R1 distilled counterparts, and looking at things like what is the per token KL divergence between the two. And they found that quite a lot of them could be characterized by a small handful of behaviors, which they list here. So kind of like what they call initialization, so like planning, deduction, so like taking all of the stuff so far and doing a step of logical deduction, factual recall that's then used, generating a bunch of examples for like additional data, stating how uncertain it is, and being like, wait, what am I doing? But, and they have this graph. I had some criticisms of the methodology, but whatever, of the frequency of each of these things in the relative models. Honestly, I would not read too much into this graph, but like the spirit is there. And importantly, when you just actually look at things like the heat maps of KL divergence between the models, it's only the kind of first few tokens in these behavioral patterns that are very different. Like once the model has said, wait, let me reconsider, it's pretty similar. This is not universally true, and it wouldn't surprise me if this is much less true for something like O3 that's gone through a lot more training. But at least for like an R1 distill, it seems like quite a lot of the difference is telling it to follow some of these reflexes, like specific behavioral patterns. And it's not that the base model doesn't know how to do them, it's that the base model doesn't know when to do them. And that a lot of what's changed about the thinking model is just learning when to perform some of these. But once it's output the like key tokens, if you just let the base model take over, it can like achieve fair amounts of the same value. And The thing they were doing in this like early draft of the paper was making steering vectors for some of these and showing that you could use them on, I think, the base model. Let's see. Nope, that's the R1 thinking model, though it does at least show that you can have a backtracking vector that makes it incredibly indecisive, or a decisiveness vector when you subtract the backtracking vector. It's so good. Or, let's see, I'm not sure if they have more fun qualitative examples, but they have graphs like this of, oh, you can insert stuff and then see what happens, though. And yes, in response to Jasmine's question in the chat, I am basically saying key tokens like weight, so, first, etc., are like kind of acting as implicit scaffolding in the model. This is still like a bit speculative, and they have not managed to recover all of the performance by solely letting the thinking model choose the scaffolding. That seems to be like a pretty big part of it. And this is like a lot of where my intuition comes from. But like, given the right scaffolding, base models are like pretty good at using lots of inference time compute. Like if you tell them to break down a task and then you give them each of the steps and you have them try a bunch of ideas and then take the best of n, etc. And, you know, conceptually, there is absolutely no reason a model can't just do this itself. It just is a difficult thing that is hard to train for and is not there naturally. Santiago?
Yeah, in this context, do you think that if instead of putting these signpost tokens, you steer in the base model with some corresponding vectors to this backtracking and certain estimation vectors, maybe not the same as you found in the chat model, but with other ones for the base, would you also get this performance recovered?
So that's pretty similar to what Konstantin and Ivan are currently working on. I think the results are like reasonably positive, but not perfect or something.
Yeah, because Ivan told me that when you do the steering with the chat vector, it doesn't work. But if, I guess, I don't know if they found something corresponding to the base vector, so corresponding to a vector for the base model.
What do you mean by a chat vector here?
The vector that you found in the chat model for steering, so the one that they found in this paper. Now, in the base, as far as I know, from what Ivan told me, that steering vector doesn't work as well. But maybe you can find a base steering vector, like a vector that does what you want, but in the base model, possibly different. And we expect that if you steer with those.
So I think that a crucial... So I think that a thing which is very important to keep in mind is that I think you can basically think of something like backtracking as a very complicated if statement, where the condition is like really messy. It's like based on a bunch of things, like how uncertain the model is, how long it's been pursuing the current thing, how recently it had some progress, things like that. How many other things it could see potentially doing, blah, blah, blah. And I imagine that there's like quite a lot of nuance in exactly when it is and is not optimal to backtrack. But the implementation of the backtracking is not that hard. So if the like backtracking circuitry fires, then it produces the steering vector. But probably the base model does not have a lot of the circuitry required for good backtracking. And that's a lot of what was learned in RL or in distillation. And so it wouldn't make sense to think of this as adding some thinking vector that makes the base model into a thinking model all of the time. But if we add the backtracking steering vector, if the thinking model wants to backtrack, we're kind of using its like if machinery, meaning the base model doesn't need to have its own if machinery. Did that make sense?
Right, and I guess one more question. So how would you compare this with the refusal vector? Because they do find, and I think there's work that you did on finding that the refusal vector from the chat transfers to the base model. And there seems to be that for refusal, there is also a complicated if statement.
So what we found was that the kind of action feature of I should refuse has a very simple linear representation. And that if you add this in, you're basically just forcing the if to be always on, and it will always refuse. Ish. And if you stop the model ever producing it, you're deleting the if, and it will never refuse. And you can, yeah, there was like some follow-up work, but we found that there was like a similar notion of this vector in the base model, a little bit unclear why, maybe because there was already some chatbot data in the pre-training data or something. But like the circuitry introduced in the chat model is like when to apply the refusal. And admittedly, like, is this thing harmful is probably already in the base model, but maybe there's some nuance that's additional, like, I don't know. Yeah, when to refuse, how to feel about it. Maybe there's some like additional corporate policies the company training the LLM has that get baked in, etc. Victor?
Yeah, so just to make sure I understood that properly, you argue that the reasoning model basically learns like if or backtracking features or circuitry, or does it have them, but learns when to apply them, or a bit of both?
Okay, so I think there's some terminology confusion here. So let's define two terms. Backtracking decision circuitry, that's like, should I backtrack? And backtrack execution circuitry. Backtrack signposting circuitry, which is like, say, wait. And then backtracking execution circuitry, which is like, if the input token is wait, actually do the backtracking. And what I'm saying is, obviously, the base model has backtrack signposting, because say wait is a trivial thing to make it do. I'm making the less trivial statement that it has backtrack execution circuitry, because if you make the model say wait, then it does a decent job of backtracking. And I am not saying that it has backtrack decision circuitry. And I am further asserting that that's actually the hard part in some sense. And I think Jim earlier asked a question about this paper that has stuck weight in places. I'm not familiar with that exact paper, but I'd assume it's something like, oh, you're just kind of designing the backtrack decision circuitry for the model. And maybe if they do something that's sufficiently reasonable, it's like actually a good approximation. I don't know. Maybe there's additional details you want to clarify, Jim?
I also haven't read the paper, so I can't really say anything.
I think
But
I
it
think I
makes
read.
sense what you say.
If it is the one from Stanford about this one, they just added whenever the chain of thought ends, they remove the end of a chain of thought token and they put wait, and they do that like 2 times.
Yeah, I mean, did they compare that to just running the chain of thought 3 times?
Yeah, they do, and it gets better performance.
Oh, interesting. Not massively surprising, but still cool. Victor?
Yeah, but I'm thinking also like the training is different, not only in okay, this is tough one. Like the goal is kind of different, right? Because in classical chat model or instruction tuning, it needs to answer questions and it needs to have a good score from humans. Whereas in reasoning model, you're trying to have it think sufficiently to find the correct solution. So is there any chance that a big part of it is not about like really the circuitry that's learned? I mean, it's still circuitry, but not really the know-how, but more just the goal of the model. And that if you were able to just change the goal of the instruction tuning to give it instruction like find the correct solution, you can think as much as you want because you won't be penalized for overlong questions. That would be enough to switch it to a very good reasoning model.
Yep. Yeah, I mean, I do agree that the goal you're training it for is like very important here. And I mean, I think one of the things that's been going on is just people have been optimizing thinking models to be good at things like reasoning and coding. And, this will obviously result in better performance on reasoning and coding benchmarks. And partially, there's been just quite important progress, and like we're getting better at these reasoning RL algorithms, and it at least seems to somewhat translate into being better at other tasks. Like, I don't know, Gemini 2.5 Pro sure just seems better at many things. And this makes sense because if the model spends more time thinking about a problem, you would expect it to get better at the problem, for like basically any problem. But to me, it seems like an open question how well these methods will result in major performance gains outside of some like fairly narrow domains. In particular, I gather that reinforcement learning, when you don't have like a kind of really clear objective reward, is pretty difficult. So like maths is easy because you just say, is this a valid proof? But something like, is this a good piece of creative writing? You can only really judge this by having another language model judge that. And it's often quite easy to hack this. And this is like a major issue in things like RLHF, for example. And yep, I have no idea how people solve issues like that. I do not work on this stuff. All right, so okay, and this also partially explains the why does distillation work, where it basically means to say the key takeaway from all of these sections is my intuition is that thinking models learn an implicit scaffold. I want to backtrack, plan, recall knowledge, etc. And this lets them productively use large amounts of inference time computed well. And then why does distillation work? Fundamentally because the strategies, or e.g. when to backtrack, are not super complicated, just hard to learn in the first place via RL. And yeah, I think that, I mean, I don't actually know whether this is just a true statement with RL in general, if like training a model with RL to do a task is hard and then distilling it into another smaller model is easy, because you just get so much more feedback when you're doing supervised learning than when you're doing RL and need to just like try strategies and see if they work and vaguely flail around action space. And if you look at things like the R1 paper, they have some interesting discussion of how the model seems to kind of suddenly learn new strategies at various points, where it kind of just never does a strategy and then starts doing it a bit and this gets good rewards, so it starts doing it way more and then it just does the strategy all the time. And I have no idea if this is just generally normal in RL or a weird thing about R1, but I thought that was like pretty interesting and notable. All right, so any closing questions on all of that stuff? Yeah, Dennis?
Yes. Okay, so I still don't quite get why it works. I mean, it seems like a bit of a miracle. In a sense, you could imagine that during distillation, well, either the teacher model produces bullshit or the learner model learns to bullshit its way and generates something well, chain of thought like, but ultimately not helpful for the task. Why doesn't this happen? Or, yeah, so why does it actually improve?
Are you saying why is something like R1 good in the first place? Or why, given that R1 is good, can we distill it into like Llama 8B?
Yeah, well, I think like these are a bunch of steps and things could go wrong at any of them. So I'm kind of surprised that it all works nonetheless.
I do share your general intuition of when you have a complicated plan, something will clearly break at some point. I guess I'd also say that when you observe something like an R1 distill working, you are not observing all of the failed experiments done along the way. So, e.g., to make R1, I'm sure DeepSeek had a bunch of failed experiments and like suboptimal experiments and botched training runs and things like that. Which is one of the reasons the like $6 million figure is wildly misleading. And it's like, it's not surprising to me that thinking models are a thing that is possible. I think that making them seems like an extremely hard technical challenge, but competent ML labs are quite good at doing random hard technical challenges, I guess. And then I guess I just don't find it that surprising that the distillation works, because so the way I think about a problem like this is it possible for the model to learn this thing? And does it have enough like training signal that it will be guided with the right gradients towards learning that thing? And to me, it just seems clearly possible that even a fairly small model could learn to be good at like deciding when to backtrack. It doesn't seem that complex. Like, I think thinking is mostly using the model's existing capabilities, though plausibly it learns some additional maths abilities or something, because I'm sure there's, even if you just fine-tuned it normally on maths data, I'm sure it would learn more things. And then, given that R1 works, it seems like it should be pretty easy to generate high-quality training data, because you just get it to solve a problem, and then this has data, and then if the smaller model is capable of imitating that data well enough, this will work. And I think that first, there's going to be a sufficiently small model that it can't learn to imitate this well enough to be useful. Like, I don't know, GPT-2 small, pretty dumb. It would not surprise me if GPT-2 small is just not capable of doing this because it lacks the long-term coherence. But especially a model that's competent enough to kind of recover if it goes off the rails, like the backtracking decision machinery misfires, it continues, but it's still speaking coherent English, and then at the next full stop, it has another chance to try backtracking. It seems like it doesn't surprise me that much that it's possible to distill in this circuit without that much data or effort. But again, this is possible and this is easy are not the same thing. I get the impression that distillation is much more idiot-proof than things like training R1 in the first place would be, just because it seems like there were a ton of replications very quickly. But, you know, there's also obvious publication bias, where you see the people who succeeded, not the people who didn't. And I haven't tried this myself, so I don't know. If any of you want to try this and tell me how badly you get wrecked, do hit me up. Useful data. Maybe even then I get a selection bias where people don't want to tell me if they do something and then get wrecked. So, who knows? Try doing an R1 distill. Okay, so I see a question from Yonel in the chat. So, likes the intuition of reasoning models learning scaffolds. Curious how you'd go about stress testing this. What experimental outcome would get evidence against? So the kind of experiment that Konstantin and Ivan have been up to is something about detecting when the thinking model wants to do one of these small handfuls of reflexes, like backtracking, and if so, making the base model do that, but otherwise letting the base model run freely on a question. And they've largely observed that this recovers a good chunk, but not all of the performance. And I think that if they'd done this and it had gone terribly, that would have been pretty strong evidence this hypothesis was false. If they'd done this and it recovered everything, this would have been strong evidence the hypothesis was fully true. Currently, I don't know, the exact percentage recovered varies a lot, depending on exactly how we do various details here. But my guess is a large chunk, but not all, is what we're going to ultimately conclude. Though people should just totally ping Ivan and Konstantin, or try to talk them into giving a talk. All right. Implications for interpretability. So nope, another question. All right, that will hopefully be covered by the ramble I'm about to give. So I think that in general, interpreting multi-token generation is substantially harder than interpreting a single token generation, because if the model generates like 3 tokens that each build on the previous one, rather than just having a single forward pass to analyze, you now have a sequence of 3 forward passes that compose with each other, going through a weird discrete bottleneck of exactly which token was sampled to go next. And this is A, just much more complicated because you now have 3x as many steps, and B, weird because rather than being a beautiful realm of linear algebra, you now have weird discretization in the middle. And it's very annoying. And what do I think? I think that a crucial reason this is hard is the whole things building on each other part. Like, if you just give the model 3 completely unrelated multiple choice questions, and then it produces 3 answers in sequence, I think that's basically fine. Because you can just think of each output token separately and not exactly fuss about the way it is building from the first ones. If the model has some really nicely encapsulated things, like you tell it what is like 100 squared minus 43, and then it first says that 100 squared is 10,000, which we'll pretend is a single token. And then it says 10,000 minus 43 is blah. Then we can now just analyze, how did it say 100,000 given what came before? And how did it say like 9,957 given what came before? And these are just 2 separate interpretability problems we can kind of analyze separately. But things get thorny when you don't exactly know what is dependent on what, and when you have really long generations, because it's kind of unclear how much you should be thinking of this as like, I don't know, there's 2,000 tokens generated as part of the chain of thought, and each one should be thought of as building on the previous ones, or actually like 90% are basically useless and just follow trivially from what came before, but the chain of thought is just very uncompressed. And then there's like 10% that matter, but actually most are kind of unrelated to the previous ones, but a few matter, and probably it's not going to be perfectly clean, and have, some tokens depend a lot on some tokens and others don't depend at all. Rather, it's going to be messier. And I don't really know. This just sounds really annoying. I'm just complaining. But I think that figuring out how to analyze multi-token generations seems pretty important to me. And in particular, there's like a few hacks you can do to try to engage with this. One would just be take a rollout, like a long generation ending in the answer, and then just analyze how each token in the rollout was produced as a function of everything that came before. This is, not that far from normal interpretability. We have lots of tokens rather than just one, but we don't necessarily need to care about this weird recursive bit. And maybe there's only a few tokens that matter. But maybe there's like 20 different paths from the question to the answer via like different rollouts. And should we care about all of them? Should we only care about the one that actually happened? Kind of unclear. I'm sympathetic to the argument that we should only care about the one that actually happened, but another question is how many of the tokens in the generation are important. So one hypothesis I have is that there's a bunch of fork tokens where the value of the token substantially changes what the model does next. Like, it produces an intermediate value in some problem and then builds on this. Or it says, it's like trying to think about a hard maths problem, and then it comes up with the key idea in the proof. I mean, there's a separate bit of messiness that often an idea is not one token, it's several tokens. But often the first token, like, almost entirely determines it or something. Like, almost entirely determines the rest of it. But I don't really know how much this fork token hypothesis is a big deal. There is a paper called Fork Tokens, which I have not read. If any of you want to read it and tell me if it makes sense, that would be appreciated. And I think this is a pretty important question. Definitely, I would be excited to see some sprints or mini projects exploring this. Let's see. I think another problem, yeah. Yeah. Are there special fork tokens to focus on, or is it all a mess of mild importance? And then, what else? Are there special fork tokens? And I think I found the fork tokens paper. All right, where was I? So, yeah. So, are there fork tokens, or is it just a mess? Is it reasonable to just study a single rollout? Well, maybe questions that annoy me and I want answers to. Will it be useful to understand where certain key tokens come from, conditional on what came before? Or will this be a total mess where insights about a single token lack much value? I think another question is just what is the algorithmic form of a thinking model? So unpacking what that means. When I'm thinking about a normal model, I'm just like, well, it produces an answer. It is either correct or incorrect. And I'm kind of trying to impose the same frame onto a thinking model. But maybe I should instead think of a thinking model as having like 20 tries at the right answer. And if it's wrong, it just tries again. Or it needs to backtrack, but it can backtrack at any point in the next 20 sentences, and it's kind of fine. And in this case, it would be a mistake to focus on the point where it decides to backtrack. And more important, to kind of try to explain why it was like inclined to backtrack for the past 20 sentences. Maybe we can get away with just not caring about this. I don't know. But it seems important. One natural way to test this would be doing things like changing the weight token to something else and seeing if the thinking model then, like, next sentence will backtrack. Or if you made it, say, wait like 5 sentences earlier, do things basically work or go off the rails? And yeah, one mental model I have for what thinking models are doing is that they're basically exploring what I think of as a tree of reasoning, where you've got a maths problem. There's a bunch of different like claims you could have or first steps you could take. And in fact, the space is like functionally infinite, but the model uses a bunch of heuristics to find plausible next steps. It then either just picks one implicitly or it lists them out and then picks its favorite. And this is like the first step it's taken. And then it kind of checks, was this useful? Have I made progress? Or was this a dead end? Did I make a mistake? And it just keeps going like this. And it keeps like thinking of what it could do next and then moving on. But sometimes it will be like, wait, I think I made a mistake. And it will backtrack and move further up in the tree. And then maybe try again. And you can kind of think of this as it doing a kind of intelligent depth first search with backtracking where appropriate. And I have no idea if this is true, but I think that you could probably have an LLM look at thinking model traces and try to break them down into a tree like this and see if the model seems to navigate it in any meaningful way. And I think this would be like a pretty interesting project. And importantly, this would suggest that if we're trying to do interpretability, maybe we should be doing a bit less in the way of interpreting like the model's trace and more trying to interpret the combination of like tree and trace. But I don't know. That is a speculative mental model. All right. Any questions, confusions, complaints on that? Yep.
So one question I had is if we have a LLM look at this chain of thought and maybe like identify some nodes in a tree,
yep,
what does this actually prove?
So the thing I would be interested in is if you have a thinking model try to solve a like reasonably complex math problem across like 100 random seeds. Can you build a like tree of reasoning from this and then visualize the kind of path taken by the model in the different times? And does this let you kind of think about the trajectory it's taking in a more productive way if you generate new reasoning traces? if, every reasoning trace is just inventing new nodes on the tree or something, then But if you could come up with a way to, at least on a single given problem, more productively understand what it does next, that seems pretty exciting to me.
Yeah.
That literally is not very useful, but I feel like if you can get that to work, there's probably a lot of room for improvement and iteration. And if you can't get it to work, that's evidence this hypothesis is false. And I'm kind of just throwing out like basic science projects at the moment. It just seems, or like basic science of LLMs projects at the moment, it just seems generally good to be less confused about what on earth thinking models are doing, given how much of a big deal they are.
Yeah, this difference between depth first, breadth first, like how to maybe operate between the two modes. Can you enforce that? That could be also something interesting, I thought.
Maybe. I think it would be quite easy. Like you just prompt it. I think that would work fine. Like you say, all right, next I'm going to think about for depth first, or okay, let me think about the possible options for breadth first. And maybe you could design some scaffolds to like make it perform a bit better or something if you did this. I don't know. But all right, I can wrap this up soon, but I'm going to try to talk a bit about faithfulness. I think this is a particularly important area. My current favorite paper on this is Chain of Thought in the Wild is Unfaithful, which I would totally recommend people check out. From Arthur Conmy's Matt 7.0 stream. So, okay, so what do we actually mean by faithful? Why do we care about this? So first off, in my opinion, faithful is an awful, awful word that we should burn with fire. And I am instead trying to use untrustworthy, which I then break down into like 5 different, more specific terms. And so fundamentally, thinking models are kind of a big deal, because now if we want to understand what they're doing, in theory, we can just read their thoughts. This is amazing. But obviously, what a model says when thinking aloud does not necessarily correspond to what it's actually doing. It could be missing important factors. This is, well, there's actually a nuance here. So there's the property of being complete, which is when the chain of thought contains every relevant factor. And then the property of being monitorable, where it contains every important factor. Like, if you read it and you understood it, you would be able to say, this is trying to take over the world or not, or something like that. In my opinion, complete is basically impossible, because there's an incredibly long tail of weird, subtle bullshit LLMs pick up on. But I think that monitorable is like maybe a more realistic property. And so you might hope that the relevant factors are in the chain of thought, and you can just read it, and it'll be glorious. But in theory, it's also the case the model could be doing all of its reasoning internally, what I sometimes think of as internalized reasoning, in contrast to reasoning aloud, externalized reasoning. And it could just be outputting either kind of irrelevant chain of thought, like it's just saying kind of random nonsense because it's doing a maths problem. Maths problems have things that look vaguely like working, and it is a good language model who cares about predicting the next token who will do this. Or it could be like producing a chain of thought that is like rationalized, like justifying a conclusion the model has come to for other reasons. Or it could be actually making a good faith attempt to talk about what's going on for it. And yeah, making a good faith attempt to actually convey its reasoning and build on this. And this is like a really subtle and thorny area when you dig into it. And I would like to at some point write a blog post on my proposed terminology for the like 20 different concepts here that should be distinguished. But if you take one thing from this, please do not use the word faithful, and be aware that people use it to mean like 5 different things. All right, so taking the specific example of this paper, which I really like, this is an example of rationalized chain of thought, where they gave the model questions like, was obscure Hollywood film A released later than obscure Bollywood film B? And when you ask it one way around, the model comes up with a reason to say yes. And when you ask it the other way around, the model like misremembers facts in order to also say yes, even though it is like clearly logically impossible that A can be later than B and B can be later than A at the same time. And this happens reasonably consistently across random seeds. I think this is reasonably strong evidence that in at least one of these cases, the model is like generating reasoning to justify the conclusion of yes that it wants to say. And I have no idea why it wants to say yes, but it does. And so it is constructing a chain of thought to justify this, which is like mechanistically how the chain of thought is unfaithful and like how it is generated. And this chain of thought is not monitorable because the fact that the wording was different changed the answer, but appears at no point in the chain of thought. And this paper has all kinds of like wild qualitative phenomena that I quite like this one of unfaithful shortcuts, where you ask it a maths question, it kind of figures out the answer by playing around with small examples and guessing, and then it introduces the delightful step of 2 plus 4 plus 8 until infinity equals -2, and justifies the correct answer by doing this. And if you ask it in another context, was this obviously invalid? It says yes, but for whatever reason, plausibly because it just associates it was like it's been reinforced to come up with like nice proofs that end in the correct answer and look kind of superficially correct. It wanted to take a sketchy step in the middle to get to the answer it had guessed but couldn't prove. And I don't know. Though admittedly a physics professor did argue with us on Twitter that this is actually completely valid maths and a perfectly reasonable approach. So I don't know, maybe Jacob wants to stand physicists as 2 plus 4 plus 8 to infinity actually being equal to -2. But anyway, so where were we? I think this is clearly extremely sketchy. And maybe that is just my opinion. Also, how does it even work? Like, this tells you that this term is negative. These two are obviously positive. But the answer is obviously positive. So how on earth do you get from this to this? Anyway, whatever. Not important. So what was I saying? Yeah, I think there's a bunch of nice qualitative examples in this paper. But importantly, I think that there's a very big difference between chain of thought is not always trustworthy and is not the same as monitoring chain of thought is not useful. And, ultimately from a safety perspective, we kind of have to be a bit pragmatic and be like, let's do things that are useful and track some valuable properties of the data. So the question is, should we expect the chain of thoughts to have any useful information at all? Anyone want to throw out some intuitions either way?
I feel like if you can show that like the chain of thought like causes the response, like that's like one way. I guess that to me is like the faithful part.
So there have been some papers that have tried doing things like edit the chain of thought and see if the model changes its answer. I personally am confused by what I should infer from this, because you are now taking a model that had a logically correct chain of thought and making it have a logically incorrect chain of thought. And this is just different. You should expect this to be different. And it's plausible that a model which notices logical inconsistencies just ignores it and falls back on other heuristics. Or it just responds to the logical inconsistency by continuing the logic because it doesn't notice. Or something like that. I don't know, I just consider its behavior like somewhat undefined here. And this reminds me, the reason that I really like this paper is while there have been other papers that show that chain of thought reasoning can be unfaithful, they do pretty contrived things, like give the model 10 multiple choice questions in the context window, whose answer is all A, and then the model starts coming up with reasons for why the 10th one also has the answer as A, even if the answer is actually B. But you would never actually do this. While was film A released later than film B is just not an adversarial prompt. This is not designed to make the model be bizarre. It just is. And they got this to work on Claude 3.7 Sonnet with extended thinking. Just wild. All right. So to me, I think that monitoring chain of thought is a pretty reasonable idea that I would be excited for companies to pursue. And the reason I think it is a good idea is that chain of thought increases a model's capabilities. And the most obvious way it increases those capabilities is that the models just explain what they're doing and explain intermediate steps in natural language. And it's a little bit unclear to me which problems need chain of thoughts to help them improve and which ones the model could do in a single forward pass anyway. If you ask the model a question like, what's 2 plus 2, it knows the answer is 4. And so it can generate reasoning for you, but the reasoning is clearly not important. And maybe it's trying to produce reasoning that is actually faithful, or maybe it's trying to forget that it knows the answer and regenerate the answer. Or maybe it's just spouting random nonsense, and then it will say the answer anyway because it knows it. But if it doesn't know the answer, then that's reason to hope that key steps must be in the chain of thought. And so concretely, I predict that the hardest problems are the ones where monitoring chain of thought is most effective. And you might hope that problems like, can I escape from the data center and steal my weights, are effective, are particularly hard. And thus ones where chain of thought monitoring would be particularly useful. Though, in my opinion, this is an open empirical question that someone should really try to answer one of these days. And yeah, I think the term, I quite like the term chain of thought uplift for how much better is the model at doing thing X with chain of thought than without chain of thought. And yeah, so I think it is a reasonable bet that in current models, chain of thought is often useful to monitor. And in particular, on the hardest problems, it is useful to monitor. But I don't think this is like always true. And I think there's like a couple of different ways things can break. So one of these is that you use different architectures, like a vector-based chain of thought, which I sometimes hear called neuralese, where rather than passing a token from the output to the input, you pass a vector. This, is not human interpretable by default. It's very annoying. There are some random papers like Coconut that are trying to do this. Fortunately, they're all very small scale. I think that if this does happen, then it will probably completely break our ability to monitor chain of thought, and be an area where mechinterp might be particularly useful if we can do something like SAEs or probes on the model to get some sense of what's going on. And I think this would be like a pretty cool question to explore, though I personally would hold off until there's more clarity on which approaches to latent chain of thought people think are most promising. Since I think there's like a bunch of random ideas out there, and I have no idea which of them are most reasonable. Another one would be alien reasoning. It's still token-based, but it is not recognizable natural language. You might hope that, like the model will continue speaking in English or insert language of your choice because it's just what it knows how to do. Like, in order to have a kind of circuit that works via generating tokens, there must be some shared language between the start and the end that they can coordinate on. And natural language is the default version of this, which is why chain of thought is in natural language in the first place. But you can totally conceive of things that could be implemented in neural network weights. Seems not great. But it seems plausible that reinforcement learning could eventually learn such things. And I don't really know what to do about this. Plausibly, giving it some penalty on things that don't look like natural language would help. Plausibly, that would just teach it to output pretty-looking thoughts. Another one would be steganography. The output looks like natural language, but is encoding information in a way that is not apparent to a monitor. Like, you could imagine, say, whether it uses a comma or a semicolon, is encoding some information to itself or something like that. Personally, I think that this is only likely to happen if we train models to have chains of thought that like look safe or something. Like, we have a monitor, and every time it does something that looks a bit sketchy, like trying to like hack a unit test or something, it penalizes it, but it still gets rewarded for hacking the unit test. So it's incentivized to figure out ways around this. And there's like a few examples by now of times when you can do this and the model will come up with codes to coordinate with itself. Like, you're training it to make loans, and it is useful for making loans based on nationality, but you have a monitor that makes sure it's not mentioning nationality, and it learns to use a subtle word choice to indicate whether it's talking about like race A or race B. And it can successfully pick up on this and make the decision, but the monitor doesn't trigger. Things like that. This seems reasonably unlikely to me unless we explicitly train for it. The main scenario that I'm scared of is that models just read a bunch of stuff about how their chain of thought is monitored and how this is a big deal, and infer that they should be encoding things in their chain of thought via some kind of out-of-context reasoning, which is sufficiently spooky that I hope it never happens, but I am freaked out that out-of-context reasoning works at all, so who knows. Another one would be, I don't have a great name for this, but I'm currently calling it DDoSing, where the model just outputs a lot of stuff in its chain of thought, of which like some bits are the crucial steps, but many of it is basically irrelevant. And this could happen, say, in the context of a maths problem, where I think that, so the argument for why chain of thought would contain any useful information is that it's easier for the model to break a problem down into steps and say, do the first half of a problem, produce the answer, then do the second half. But there's no reason the model can't also have like 100 fake answers surrounding the one real answer, somehow know where the real answer is and look at that. Or like it outputs complete gibberish reasoning or like superficially plausible reasoning and then like the correct intermediate equation, and then uses the correct intermediate equation and ignores all the random nonsense. And are there other examples? I guess there's also just like irrelevant chain of thought. COT was not needed, and just independent of the answer. This is a thorny one because sometimes the chain of thought will just be wrong, and sometimes the chain of thought will be right. But mechanistically, this seems like it should be very different from the model is doing good faith chain of thought. Another one would be rationalization, like I was talking about in the context of the paper. COT was produced to justify an answer the model had for other reasons. And there's probably more, but those are the 6 coming to mind right now. As noted, please do not use the word faithful. It should not have at least 6 meanings. To Jim's question, people have tried a bit to train probes for unfaithful chain of thought. I mean, it's a sufficiently obvious idea that I'm sure lots of people have tried. I know that in Arthur's paper, they tried a bit and it worked okay, but not amazingly. If you tag like Ivan or something in random, you can probably share more details. But yeah, is I?
Yeah, for our mini project with Yeo, this is exactly what we did as well, and it worked really well with QN 1.5b, the small model, which was interesting, but it didn't scale well to Llama 8b experiments.
Interesting. How did you get the labels?
So the labels were thankfully directly from this exact paper you showed, from Ivan's paper. Yeah.
Interesting.
And yeah, like looking at that, one thing I realized is like data creation for this task is very difficult, precisely because faithfulness is very difficult to define.
Yep. Yeah, I feel like there's some projects I would be excited about that are using things like gradients or interventions or something to figure out like, is the chain of thought irrelevant or like used or something like that. Like, it feels like there should be some attention heads which attend to the chain of thought when it's being used, but not when it isn't or something. But I think this is like fuzzy and hard to define. One case which I think probably is irrelevant to chain of thought is answer flipping, where the chain of thought justifies answer A and the model just randomly gives answer B at the last minute, which is a decent fraction of the weird instances found in the chain of thought in the wild paper. I think they got like a nice frequency table somewhere. But yep. Yeah, I think I totally recommend just looking at some of the qualitative examples in this paper and seeing if there's anything you'd be interested in exploring, because they are weird. One tip is they kind of optimized the paper for being on frontier models, but a lot of the phenomena work on smaller models. You just have to have like dumber questions. Like, I think if you ask which has a higher atomic number, magnesium or aluminium, that trips up some of the smaller models, but not the frontier ones. But if you ask about way more obscure things, it trips up the frontier ones. And yeah, if you tag like Arthur or Ivan, I'm sure they can point you in the right direction. Yeah, you definitely would like to work on a smaller model if you want to do this stuff. All right, I will probably end there. Thanks everyone for coming and bearing with me for like more than an hour and a half. I hope this was interesting, and I will close with the take that you should remember there are non-thinking model approaches during the sprint. This is an option, but they're also very interesting. So I'm totally happy to have some. And it sure would be embarrassing if we just completely fail to understand how to interpret these. All right, see ya.